There are categories in which geometry is somehow tame. For instance, when we work with polynomials or real analytic functions or complex analytic functions. But there are some other categories in which the general study of geometrical objects is a nightmare, as for instance, like in the C-infinity category. If you consider a closed subset of Rn, then that can be obtained as the zero set of a C-infinity function. So essentially, for instance, if we consider the intersection of two submanifolds in the C-infinity category, it can be almost anything. It can be, for instance, a counter set. So we have to develop new concepts so that these intersections are actually well behaved. And that's what we're going to do in this lecture. We are going to define the notion of transversality. First of all, we are going to consider again the situation for submersions, because our approach to transversality is going to be via submersions. Consider L differentiable maps, G1, G2, GL, from a differentiable manifold X to R. And we have that the differential of every single one of them at the point X is a linear map from the tangent space of the manifold at the point X to R. Or if you prefer, it's an element of the dual vector space of the tangent space of the manifold at X. What happens is that the map G, whose components are the Gj, is a submersion at X if and only if these differentials are linearly independent. If we consider this map in local coordinates, the Jacobian matrix of G at the point X is going to be of the following form. It's going to be a matrix whose dimension is L times M, okay? And the first L is less or equal than M. The first line is going to be the differential of G1 at the point X. The second line, the differential of G2 at the point X, and so on. And what happens is this Jacobian matrix has maximal rank if and only if the lines of the matrix are linearly independent. And so if and only if the differential of the components of G at X are all linearly independent. Something else that we can actually point out is that we have this equality. What happens is that first we are going to consider these two linear subspaces of the tangent space of the manifold at the point X. And the first thing that we are going to calculate is the dimension, right? Since G is a submersion at the point X, the dimension of the tangent space of the preimage of G of X at the point X is going to be what? We know what because of the, for instance, the properties of submersions, we know that this dimension, that this linear subspace has codimension equal to L. So the dimension here is actually M minus L. If you consider the dimension of the intersections of the kernels, okay, here I was using the notation for Portuguese, but these are the kernels of G sub j at the point X for j between 1 and L, this dimension over here of the intersection is also equal to M minus L. And it's there where we are using that all these maps are linearly independent. That's the reason, because the intersection of the kernels has dimension M minus L. So in this way, we have two linear subspaces whose dimension is the same. That's good. But now that we know what the dimension is, let's point out that if we restrict the differential of G at the point X at the tangent space at X of G minus 1 of G of X, okay, that's actually the zero map. And the reason is that restriction can be obtained actually by considering the differential of the restriction of G to G minus 1 of G of X. But this is a constant map, and the image is indeed the point G of X. This is a constant map. And so the differential is zero. And that's the reason that we get exactly this. Now, let's realize that the differential of G at X is the differential of G1 at X and so on till the differential of GL at X. So the kernel of this linear map over here is the intersections of the kernels of all these maps. Note here is for kernel. And so what we actually proved is that the space to the right is contained in the space to the left. But since both of them have the same dimension, they are the same. So the tangent space at the point X to G minus 1 of G of X is the intersections of the kernels of the GJ maps, the differential of the GJ maps at the point X. We are going to use later on this result. Okay, so what we want is generalizing this concept of submersion to study more general situations. Like, for instance, the one that we are introducing right now. Consider a differentiable map F from the manifold X to the manifold Y, and let C be a submanifold of Y. What we want is to know, if possible, when the preimage of the submanifold is indeed also a submanifold of X, and whether or not there is a natural sufficient condition. Of course, we don't want to know when the preimage is a submanifold in every case. We want that, but that would be incredibly hard to do. The case that we know is the case in which C is indeed a point. And in that case, the sufficient condition is that P is indeed a regular value of the map F. Okay, or if you prefer to let's say unwrap that concept, what we want is that at every point of the preimage of P, F is indeed a submersion. Okay, and this is clearly a local problem. In order to know whether or not the preimage of C is a submanifold, it suffices to study at the neighborhood of every of its points. So we can actually consider local charts and translate this problem into a problem of differentiable maps between open subsets of Euclidean spaces. That's not going to be an issue at all. Okay, if we have a point Y of the submanifold C, let's assume that the codimension of C is equal to L, we are going to have submersion defined in an open neighborhood U of Y in our manifold big Y, such that the perimeter of zero is the intersection of the domain of definition of G with C. That's the kind of thing that we get by considering local coordinates in which the submanifold has a nice form. What do I mean by that? If you fix the point Y, there exist local coordinates in our case x1, x2, xm. The local coordinates are just the components of a local chart, such that locally C is actually given by the zeros of the L first coordinates. We always have that if the codimension of our submanifold is equal to L. And indeed, the function G that we have to consider is the function that sends the vector x1, x2 till xm to x1, x2, xl, which is actually the local normal form for submersion. Okay, that's the situation we are in. Okay, and what happens is that a necessary condition so that the preimage of C, let's consider this situation in which Y is a point of C and we consider a point X in the preimage of Y. The condition that we need, the necessary condition that we need that it's naturally deduced from what we already know to ensure that the preimage of C is a submanifold in the neighborhood of X is simply that the composition of F and G is a submersion at X. Then you use the properties of submersions and they tell you that the preimage of C is going to be a submanifold of X of codimension L because this is a map from X to RL. Okay, so that's what we need. But obviously there is a problem with this condition. It's that it depends, theoretically, at least a priori, on the choice that we made for G. So if we can actually somehow write down that condition without using G, that could be good. If we can actually have an expression of such a condition that is intrinsic, then we are going to be in a much better place. So this is a picture of our situation. What we want to understand is whether the preimage of C is actually a submanifold of big S in a neighborhood of a small x. Here we have our map F, and there we have the submanifold C of big Y. And what we consider here is a submersion G that sends Y to RL and C is sent to 0. And so the points that are sent by F to C are the points that are sent by the composition to 0. Okay? That's what we are considering. And what we want is understanding when the differential of the composition of G and F at the point X is a surjective map. In order to do so, we consider the chain rule. The differential of that composition at the point X is just the composition of the differential of F at the point X and the differential of G at the point Y. Y is just the image of X by F, okay? And we know that the kernel of the differential of G at the point Y is just the tangent space of C at the point Y. We just saw that in one of the first slides. So what's going to happen is that the composition is going to be a submersion at X if and only if the image of the differential of F at X plus the tangent space of C at the point Y is equal to the tangent space of big Y at small y. So we have a map, just the differential of G at the point Y between the tangent space to big Y and small y to RL, which is surjective because G is indeed a submersion. And what we want actually is restricting this map to the image of the differential of F at the point X. And the condition that we actually need is that this restriction is still surjective. But this is going to happen if and only if the image of the differential of F at the point X plus the kernel of the differential of G at the point Y, this sum is the whole tangent space of big Y at small y. That's it. If this happens, it's because that map, this restriction is surjective and the other way around. And so now, yes, what we have to realize is that this kernel is just the tangent space of C at the point Y. And that's the reason we get the transversality condition. This is the transversality condition. The image of the differential of F at X plus the tangent space of C at Y is the tangent space of big Y at small y. Okay? So we use this idea to define properly transversality. Let F be a differentiable map and C a submanifold of the target space of codimension L. And we say that F is transversal to C if for every point X in the domain such that the image is in C, then we have the condition that we just introduced. The image of the differential of F at the point X plus the tangent space of the submanifold at the image of X is equal to the tangent space of N at the point F of X. If we have that for every X such that its image by F is in C, then we say that the map F and the submanifold C are indeed transversal, are indeed transverse. So this is the notation that we are going to use. If F is transversal to C, then we write it this way. And what we get because of the, because of a consequence of the discussion that we just had, is that if we have a differentiable map and a submanifold of n of codimension L, and we suppose, of course, that F is transversal to C, then the preimage of C is a submanifold of M of codimension L. So we actually have the necessary condition we were looking for, and it's transversality between the map and the submanifold. Here, we are going to consider a couple of examples. In these two examples, the domain M is the line, the domain of our maps. The target space is the plane. The submanifold is the x-axis. And the maps are these two maps over here. A map parameterizing the y-axis in the first case, and a map parameterizing this parabola over here in the second case. What we have is that in the first case, the map F is actually transversal to C. And it's very easy to calculate this because the tangent space, okay, the image of the differential of F at the point X is just the y-axis. Whereas the tangent space of C at the point Y, or the point, okay, here I'm X, Y, what are these? What we have to check out is the points X such that f of X belongs to C. But the unique point such that its image belongs to C is 0. So what we have to write here is 0. And the tangent space that we have to consider for C is the tangent space at the image of 0, which is the tangent space at the origin, okay? And this tangent space, it's going to be the x-axis. And the sum of these two vector spaces, these two vector subspaces, the y-axis and the x-axis, is indeed the plane. So F is transversal to C. In our second example, the unique value of T such that the image belongs to the x-axis continues to be 0. And so we have to calculate the image of the differential of F at 0 and the tangent space of C at the origin. Here we have that the second one is the x-axis, but the first one is also the x-axis. And so the sum of these two linear subspaces is the x-axis, which is not R2. So we are in a situation in which there is no transversality. And this corresponds intuitively with the notion that we have of a transversal intersection of two curves. Indeed, we can use the definition we gave of transversality between a map and a submanifold to define when two submanifolds are transversal. We consider X and Y submanifolds of a manifold M, and we say that X intersects Y transversally if this inclusion map from X to M is transversal to Y. Theoretically, this notion is not symmetric. A priori, let's say very a priori we could have that X could be transversal to Y and Y couldn't be transversal to X, but that's never going to happen because if you take a look to this condition, what what we have is that for every x, that condition says that for every x such that belongs to, for every small x that belongs to big S, such that the image of a small x by the inclusion, which is still x, belongs to y. So for every point in the intersection, what we get, this is the condition of transversality, is that the image of the differential of the inclusion at the point x plus the tangent space of y at the point x has to be the tangent space of M at the point x. That the image by the differential of the inclusion at x is indeed the tangent space of big X at small x. And so we have this condition over here. And this condition is symmetric. So if x is transversal to y, then y is transversal to x. Okay? In this lecture, we introduce the most important definition in this course, the concept of transversality. In next lecture, we are going to see some examples, and moreover, we are going to prove an interesting result, namely that the transversal intersection of submanifolds is still a submanifold of the expected dimension. Thank you for your attention.